So today we're going to be talking all about water and the various properties that water exhibits. So you may ask, why are we talking about water in biology? And it's because roughly 70% of our body is composed of water. So our cells are filled with and surrounded by water, and water's job is going to be to transport substances in and out of our cells. And this is going to make water essential for life because we're made of 70% water. Our cells have water and are surrounded by water. And the job of the water is to help transport things in and out of our cells. If that didn't happen, we couldn't live. So water is going to be essential for life. Our last time we talked about water being a polar molecule. Remember, a polar molecule means that a molecule has a positive and a negative end. So here's a water molecule with an oxygen and two hydrogens. We have one oxygen atom and two hydrogen atoms that are covalently bonded together. That means that the oxygen and the hydrogen are going to share electrons. Remember, covalent bonds are really strong because they share electrons. Oxygen is more electronegative. Electronegative means that oxygen likes electrons more than hydrogen. So oxygen atom wants to keep those electrons really, really close. And we talked about if you keep something negative close to you, you're going to become negative. And it's pulling the negative away from the hydrogen, therefore the hydrogen is going to be positive. So this dynamic of oxygen holding electrons closer, that's what creates the positive and negative poles. And this is going to allow water to hydrogen bond to one another. And the way this works is that your positive is attracted to the negative. The positive is attracted to the negative. So I have a negative oxygen there. I have a second water molecule with an oxygen that's negative and two hydrogens that are both positive. The negative oxygen is attracted to this hydrogen. It's going to make them stick together. And that therefore water is going to be a sticky molecule because it wants to stick to things that are charged. So water is polar, and that allows it to make hydrogen bonds. One way that I help students remember the charge on the oxygen versus the hydrogen is an H looks more like a plus than the oxygen. So since the H looks more like a plus, it's going to be positive. And again, opposites attract, so positive and negatives are attracted to each other. Therefore, they're going to stick together. And this dynamic of water being polar and wanting to stick together is going to give it several unique properties. We're going to talk about each in detail, but first we're just going to start by talking about them in general. So water itself has a high specific heat, meaning it stores heat relatively easily. So in the summertime, the ocean is going to warm up. It's going to take a while to warm up. Sometimes you can go in June and the water's still a little chilly because it takes so long for the water to warm up. But then when it starts to cool down in September and October, the water is still relatively warm because it takes a long time for the water to lose that heat. That's an example of high specific heat. Water also exhibits cohesion, meaning water sticks to water, so it sticks to itself. Cohesion means two like things sticking together, so water sticks to itself. Water is also going to stick to other things, which is adhesion. So water sticking to other things is called adhesion. When water freezes and becomes ice, the ice is going to float on top of the water because the ice is less dense when it's a solid. So ice floats because it's less dense. Water is also known as the universal solvent, meaning that it's going to dissolve and transport many different molecules. So water dissolves and transports many different things, therefore it's called the universal solvent. Okay, we're going to now go through each one in more detail. So the first one we talked about was high specific heat, meaning water heats slowly, but it retains heat longer than other substances. This is why it takes a long time for water to warm up, but it also takes a long time for it to cool down because it retains heat longer. And it's going to resist any changes in temperature. And the reason why this is important to life, one is because due to climates. We talked about the coastline. Typically, the coastline is going to be cooler. So if it's a really hot summer day and you're here where we live and it's like 100, if you were to go to the beach, it could be 70s or 80s because the water is going to help absorb the heat, making it cooler. So this is going to help moderate climates. High specific heat is also important in a process known as evaporative cooling. So essentially what that means is that organisms are going to sweat, so humans sweat. We release water. The water is going to evaporate from our skin, and that's going to cool us down. So we talked about in Unit 1 how the ability for humans to maintain a constant, stable temperature is called homeostasis. Therefore, sweating and evaporative cooling is going to help regulate our temperature, therefore helping us maintain homeostasis. So this is a very important property of water, that when it evaporates, it cools off the organism. Property number 2 was cohesion. And again, cohesion is when two like things stick together. So the ability of water to stick to water is called cohesion, water sticking to water. So over here, if you were to put drops of water on a penny, they wouldn't want to fall off because the water wants to stick together. So it causes this big bubble on top of the penny. And cohesion is going to be important because it's going to cause surface tension. So if you've ever seen bugs walk on water, or sometimes really heavy things have the ability to float, this is due to surface tension. So cohesion at the surface of the water causes the water to stick together on the surface. And this is why you can get these cool images. Let's see if we can find one of a swimmer coming out of the water. We'll see if we can find a cool image. Here we go. Let's check this one out. So you can see how the water has not broken as this swimmer is coming out of the water. And that is because of surface tension, which is the thin film at the top of the water caused by cohesion. And that's going to allow bugs the ability to walk on water. The next property of water we're going to talk about is called adhesion. Adhesion is the ability of water to stick to other things, so different substances. If you think about tape, tape is an adhesive, meaning it sticks to other things. Therefore, adhesion is the ability of water to stick to other things. This means water can form hydrogen bonds with other molecules other than water. So you might see this as, if you're measuring something in a graduated cylinder, it causes this meniscus, which is this like U-shaped curve here. And that's because the water is actually climbing up the sides of the graduated cylinder due to adhesion. It's also why water climbs up a paper towel. It's why you can sometimes see water little droplets sticking to leaves, or you also notice it if it rains or something and you go out to your car, you have droplets of water stuck to the windshield even though the window is straight up and down. It's because water is adhesive and sticks to other things. When adhesion and cohesion are working together, it causes a property called capillary action. So capillary action is when water is cohesive and adhesive together, and it's going to help water travel against gravity up a thin tube. So this happens in plants, but this is also how diabetics are able to take a blood sample. They use capillary tubes, and it is a very thin tube, and the blood will go up the tube against gravity. And the way this works is the molecule of water will stick to the side of the tube, and as it moves up, it's going to pull the other water with it. So it's adhesive and sticking to the side of the tube, and it's cohesive because the water molecules stick together. So over time, it's going to travel up and up and up. In plants, this happens in the stems of plants, and it's aided with the process of transpiration. So back to ecology, transpiration was the evaporation of water from a plant, and this is going to help water be pulled up the stem of the plant as well. All right, so property number 4 that we talked about is water is less dense as a solid. And what this is going to cause is ice floats. When water freezes and becomes a solid, it's going to form this perfect crystalline structure. And that perfect crystalline structure is going to cause water to be less dense when it's frozen in the form of ice. Therefore, ice floats in liquid water. And you might be asking, well, why does that matter? Well, this is why oceans and lakes don't freeze solid. And while that might not seem like that important of a thing, it is very, very important. So let's think about it this way. What if ice sank? So if ice sank, when it got really cold outside, it was wintertime, a thin film of ice would form on a lake. Let's say that ice sank. So it sank down to the bottom of the lake. 2 things would happen. It would either A, crush anything below it as it went, or if it didn't crush everything, it would take away the insulation. Because what ice does on the top of a lake or on top of an ocean, it's going to insulate and store heat to allow the living things to survive. So if the ice sank, it would either crush the things living below it, or it would take away that insulation. The whole thing would freeze solid, and all the living things would literally freeze to death. So the way that we can actually have aquatic environments and ecosystems is because, in one part, because ice floats. It insulates everything below it so that everything does not die. Right, the last property of water we're going to talk about is water being known as what is a universal solvent, which means water is really good at dissolving and transporting other polar or charged molecules. So anything that's charged or anything that's polar can be transported and dissolved by water. So when we're talking about things mixing together well and dissolving, there are a few terms you might hear. The one that we've been mentioning is solvent. A solvent is a liquid that's going to dissolve something else. The thing that you're dissolving, the solid that is being dissolved, is called the solute. And the whole mixture together is called a solution. So let's apply this in terms of Kool-Aid. I like Kool-Aid. So the solvent in Kool-Aid is going to be the water. The Kool-Aid powder is the solute, and the whole mixture, or my drink, is the solution. So again, polar things dissolve in water. The reason why this happens is because polar molecules are hydrophilic. Hydro means water, philic means likes. So polar molecules likes water. They stick together, they dissolve well. Things that are nonpolar essentially means not charged. They are hydrophobic, meaning hydro means water, phobic means doesn't like. They don't like water, therefore they don't mix together. And an example of something that doesn't mix with water would be oil. So if you've ever done cooking and you put some oil in your water, the two separate. They clearly separate. Therefore, oil is not charged, water is charged. They can't mix. Oil does not like water. This is also why if you've seen that little trick where someone puts like a pepper in some water, they stick their finger in it and the pepper spreads out away from their finger. The way they do that is by putting like oil or soap on their finger. They put something non-polar on their finger and it causes the water to rush away from their finger, taking the pepper with it. It's not actually a magic trick. They're just using properties of water to trick the brain. The importance of this in life, of water being a universal solvent, is because water is going to be able to dissolve things. Let's say in your blood. Your blood is mainly made of water. The water in your blood is going to dissolve many different proteins and nutrients and then transport them throughout your body. And that's going to help us stay alive by transporting things throughout our bodies. This dynamic is also functional in the cell membrane, transporting things in and out of cells. Okay, so those were the properties of water. We're going to switch gears a little bit here now and talk about the pH scale. So here's an image of the pH scale. We may have seen it before, and we're going to go through it here in just a second. But first we're going to talk about what pH is in general. So pH, the pH scale, is a way that we measure the amount of hydrogen ions in a liquid, and that's going to tell us how acidic or basic that solution is. So all liquids are going to have a pH, meaning they have some measure of hydrogen ions. The amount of hydrogen ions is going to contribute to if that solution is acidic or basic. There we go. So we have 3 different categories that a liquid can fall into on the pH scale. A liquid can be neutral. Neutral is a pH of 7. Now you're going to notice on 7, the only thing that is neutral are things that are based in water. So distilled water is neutral, and water is going to be the only substance that falls into our neutral category. And when we're looking at our pH scale, our number goes from 0 all the way up to 14. So 7 is perfectly in the middle, and it is called neutral. Solutions could also be acidic. Solutions that are acidic have a pH between 0 and 6.9. So the way that I like to remember this, it can be like a number scale. They go in alphabetical order. Acids come first, 0 to 6.9 are acidic solutions. They could also be basic or alkaline. Alkaline and basic mean the same thing. Alkalines or bases have a pH of 7.1 to 14. So above 7 are going to be your bases. The closer you are to 0, the more acidic you get. The closer you get to 14, the more basic you get. And you can see some general trends here. If you look on the acidic side of the scale, we see things like battery acid, lemon juice, wine, normal rain, coffee. Things that we actually consume are typically acidic. So tomato juice, tomatoes, oranges, those are all acids. Now, just because we consume them doesn't mean you can consume everything on the pH scale. The more acidic or the more basic you get, the worse it becomes for you. So strong acids can literally eat away tissue, and so can strong bases. So both can be very corrosive. If you were to look at the basic side, we see things like baking soda, soft soap, ammonia, lye, bleach. So a lot of our cleaners are going to fall on the basic side of the scale. The importance of the pH scale for life. Most substances within the human body are going to have a pH between 6 and 8. So they're relatively neutral. The only exception to that is in the human stomach. Our stomach has very strong acids to help break down things that we eat. So our stomach can have a pH as low as 2. Now, while we do have something very acidic in our bodies, that does not mean that our whole body can tolerate things being a pH of 2. Our stomach is very unique in the fact that it can tolerate such a low pH. If the stomach were to actually burst and this acid were to leak out into the rest of our bodies, it would kill us because it would break us down from the inside out. Don't think that just because our stomach can tolerate pH of 2 that everything else can tolerate a pH of 2, because that is not true. So life cannot exist in environments that have a too low of a pH or too high of a pH. So anything too acidic or too basic can be detrimental to life. So basically, we're just going to go through a review of everything here. The take-homes. Water is polar. Because water is polar, which means charged, it has lots of properties which make life on Earth possible. Without water being polar and having all these properties, it would be hard for life to exist as we know it. So the chemical behavior of water is going to help how we function. We function the way that we do because water works the way that it does. And that is why water chemistry is going to be the basis of life, because again, our bodies are made of 70% water. So we're going to do a few review things here. So it says draw the hydrogen bond between two water molecules. I don't have space to draw that, but if you were to scroll up here, I did draw that bond here. So what we did right here, this is number 1 of the review section. Drawing the attraction, it's also located in this image right here. So this is number 1 from the review section. Let's see. Number 2 out of 5 is partial to life. I don't have room to write them all, but again, we can back up here and they're listed here. Water has a high specific heat, meaning it can store heat. It is cohesive, meaning water sticks to water. It is adhesive, meaning water sticks to other things. It is less dense as a solid, meaning ice floats. And water is also the universal solvent, meaning that it can dissolve and transport many different other molecules. Number 4, define pH and give some examples. So pH is going to be the measure of the amount of hydrogen ions in a solution. And this is going to make things either be neutral, acidic, or basic. And how acidic or basic things are going to depend on their function within our bodies or outside of our bodies and how we tolerate it. Why is the pH scale important in living organisms? It's important in living organisms because most living things can only tolerate a small range of the pH scale. In humans, it's going to be roughly between 6 and 8 on the pH scale. And lower pHs are only useful in our bodies in the stomach, but that pH cannot be tolerated elsewhere. So pH stability is important in living things because if something was too acidic or too basic, it would lead to death. All right, so we're going to have some practice, some matching and everything with these properties of water. So just check that out on Canvas.